With cryptocurrencies, a Merkle tree database is used to securely split the block's data and ensure that it is not lost, damaged, or altered. This method of data management makes it possible to validate specific transactions without downloading the entire terabyte-sized blockchain. It is a reliable, secure, and cryptographic method of running the blockchain. Ralph Merkle, a computer scientist renowned for his work on public key cryptography, proposed Merkle trees in the 1987 paper, A Digital Signature Based on a Conventional Encryption Function. Merkle tree is a hash-based mathematical data structure that compiles the summaries of all the transactions in a block. It is a method for quickly checking the accuracy of data in a decentralization manner. As a result of its functionalities, Merkle trees are utilized more effectively and securely to encrypt blockchain data. Merkle trees are often used with peer-to-peer networks because of the need to have information shared and independently validated. Let's understand more about Merkle trees and how they work. The Merkle tree, also known as a hash tree, has a binary tree structure, with the hashes of the transactional data on the bottom row being referred to as leaf nodes, the intermediate hashes being referred to as non-leaf nodes, and the hash at the top being referred to as the root. Even though the majority of hash tree implementations are binary, each node has two child nodes. They can also have a lot more child nodes. When looking at the structure of a Merkle tree, all transactions are grouped in pairs. Each pair has a computed hash that's stored directly in the parent node. These nodes are also grouped into pairs, after which their hash is stored on the next level up. This process continues until reaching the root of the Merkle tree. Let's take a look at each of the nodes. Leaf nodes are the hashes of each cryptocurrency transaction in a block, also referred to as transaction IDs. You view the transaction hash when you search for a transaction on a block explorer. Non-leaf nodes, in contrast to leaf nodes, merely store the hash of the two leaf nodes that it represents and don't contain transaction IDs or hashes. As a result, there will be half as many hashes or nodes in the non-leaf node layer above the leaf nodes as there are in the leaf node layer. As the tree narrows as it ascends, these non-leaf node layers continue to be hashed together in pairs, resulting in half as many nodes per layer. Two nodes will be present in the final non-leaf node layer. This creates the Merkle root and is the location of the last hashing in a Merkle tree. With Bitcoin, the hashes of all transactions are combined into a single hash and stored in the block header. The Merkle root, also known as the root hash, is this particular hash. The leaf nodes at the base of the Merkle tree can be verified using this Merkle root. When used for cryptocurrencies, the Merkle root makes sure that data blocks are unaltered, undamaged, and whole. A Merkle tree is binary, which means that the total number of different leaf nodes must be even for the tree to be properly constructed. When an odd number of leaf nodes exists, the previous hash will be duplicated to provide an even number of nodes. How does a Merkle tree work? A Merkle tree is essentially designed to break large pieces of data into considerably smaller chunks, which ensures that all the transactions can be verified promptly. The tree summarizes every transaction by creating a small fingerprint of a specific set of transactions, which makes it easier for users to verify the availability of transactions in a block. Merkle trees are formed by hashing different pairs of nodes until just one hash remains, which is referred to as the Merkle root. These trees are built from the bottom up, with each transaction consisting of hashes. Every leaf node is a singular hash of data. As for non-leaf nodes, these are hashes of previous hashes. Let's say that a Merkle tree consists of 4 transactions which are labeled D0, D1, D2, and D3. Each transaction is hashed before the hash is stored directly on the leaf node. When this occurs, hash N0, N1, N2, and N3 are created. Any consecutive pair of leaf nodes will then be summarized in a parent node via the hashing of hash N0 and hash N1, which results in hash N4. If hash N2 and hash N3 are hashed together, hash N5 is created. Both of these hashes, N4 and N5, are hashed once more in order to create the Merkle root. This process can be used with extensive data sets. The Merkle root is responsible for summarizing the data that's present in specific transactions, all of which are stored directly in the block header. This technique results in data integrity being properly maintained. In the event that one detail within the transaction is changed at some point, the Merkle root will automatically change alongside it. Benefits of a Merkle tree. 1. It's easy for transaction integrity to be verified in practically no time at all. Because of how the data is structured, very little memory needs to be used during the verification process and the computing power required is significantly reduced. Because blockchains typically consist of hundreds of thousands of blocks, each of which can contain up to several thousand transactions, validating the data poses two major challenges: memory space and computing power. Every node on the network would have been required to maintain a complete copy of every transaction that has ever taken place on the blockchain if Merkle trees were not a concept in the blockchain. A node would have had to compare each entry line by line when verifying a transaction to ensure that its records exactly match the network records. The network's security could be jeopardized if there was any discrepancy between the records. As a result, to compare the records to make sure there had been no changes, the computer used to validate the data would have needed much more processing power. Merkle trees, on the other hand, offer a solution to this issue by drastically reducing the amount of data that must be kept on hand for verification needs. They hash every entry in the ledger, effectively separating the data itself from the evidence supporting it. A Merkle tree is essentially a great way to demonstrate that something is present in a dataset, without having to download the entire set. Consequently, less computing power is needed to validate the transactions. 2. As a result of the distribution of the transactions on the block among the validators, each validator is working on a different transaction at the same time. Compared to a method where each transaction is sequentially validated after another, this is much more effective. 3. Simple payment verification, which enables you to confirm a transaction without downloading an entire block or blockchain, is made possible by the Merkle tree. This enables the use of a light client node, more formally known as a crypto wallet, to send and receive transactions. 4. The hash structure makes it easy for miners to identify if tampering has occurred with transactions. A distinct hash value is generated for each block using the Merkle root. The block links one block to another in the blockchain by including the hash of the preceding block. The hash of any transaction changes whenever that transaction is modified. The block becomes invalid as a result of this change because it cascades up to the Merkle root and alters its value. This then causes a change in the hash of the following block, rendering the remainder of the blockchain invalid. As a result, the Merkle tree creates an immutable record of the block's transactions. Why are Merkle trees important in blockchains? Merkle trees have proven to be essential for blockchain technology because they facilitate quick and easy verification in a manner that's not possible with other techniques. These Merkle trees provide developers with the ability to compress exceedingly large sets of data by getting rid of all unnecessary data and turning the data that remains into hashes. Bitcoin uses Merkle trees in several ways, which makes these trees integral to the entire Bitcoin platform. In fact, these trees are present in every Bitcoin block header. The hash for every transaction that's available within the block is placed in the header. When it comes to Bitcoin, the Merkle root is important for mining as well as verification. Bitcoin blocks consist of headers that contain metadata as well as an extensive list of transactions. This list is usually larger than the block's header. Miners hash data to create an output that adheres to specific conditions, which is necessary when validating a block. The miners can make trillions of separate attempts before they find a valid block. Every attempt requires a number in the header of the block to be changed. Even though thousands of separate transactions can exist in a block, each one must be hashed. Another aspect of the Merkle root that's used with Bitcoin involves leverage, which focuses on light clients. When a node is being operated on a relatively weak device that has limited resources, users won't be able to download and hash every transaction in a single block. Instead, a Merkle proof can be requested, which is confirmation that a transaction is present in a block. By reducing the number of hashes that need to be performed during the verification process, verification can occur without using as many computing resources. Ethereum is based on a somewhat modified version of the Merkle tree, which is why it's referred to as the Merkle-Patricia tree. Every block within the Ethereum blockchain consists of 3 Merkle trees, as opposed to one binary tree, which is what happens in Bitcoin blocks. Each of the 3 roots has its own purpose. The initial root is considered to be the root of every transaction. As for the second route, it shows the state of the transaction. The final route is the receipt of the transaction. A user can look at a Merkle route to determine if a transaction is found on a specific block, as well as determine what their account balance is.
If you found this article useful, please consider subscribing to our YouTube channel. You can also visit our website, where you find great educational contents about cryptocurrency. As a member of our Cryptocurrency Academy, you'll have access to exclusive resources and tools to help you stay informed and make better trading decisions. Additionally, discover and join our Discord. Our Discord server will provide a supportive network of like-minded individuals who can provide guidance, advice, and encouragement.